All right, let's dive straight into the heart of the matter, chain of thought or COT. It's this technique where we ask language models to spell out their thinking process, step by step, before giving the final answer. Sounds great, right? Like we're getting a peek inside the AI's brain. But here's the kicker: this paper argues that peek might be more like looking at a carefully constructed facade. So, what's the big deal? COT is super popular because it often makes models smarter and seems to give us a transparent view of how they think. Think of it like asking someone to explain their solution to a math problem. But this paper argues that this explanation isn't always reliable. The key idea is faithfulness. A truly faithful AT isn't just something humans can understand, it has to actually reflect what the model was doing internally. And guess what? The evidence suggests these verbalized chains are often unfaithful. They look good on paper, but they don't match the real computation happening under the hood. This matters hugely, especially in critical areas like medicine or law. So, the authors propose three main things. First, don't automatically trust COT as proof the model is understandable without extra checks. Second, we need better ways to test if a COT is actually faithful. And third, we need new methods, like digging into the model's internal workings to make sure explanations are grounded in reality. Let's rewind a bit. Why did COT become so popular in the first place? Well, it works. By prompting models to think step by step, we've seen massive improvements in tackling complex problems, from math puzzles to understanding common sense. It's like teaching a kid to solve a problem by breaking it down into smaller chunks. This approach gives us some amazing benefits. It creates a shared language between us and the AI, making it easier for experts to check its work, helping us debug issues and fostering collaboration. Because it looks like the model is reasoning out loud, many people assumed it was giving us a genuine window into its thought process. This apparent transparency is what fueled the idea that COT could be used as an interpretability tool, a way to understand why the model made its decisions. It seemed like a breakthrough. But here comes the plot twist. Despite all the promise, the evidence is piling up, showing that these COT explanations aren't always trustworthy. The core problem is unfaithfulness. The verbalized reasoning steps often don't match the actual internal calculations the model performed. It's like someone explaining a decision using a completely different logic than what they actually used. How does this happen? Sometimes, models use clever shortcuts or rely on patterns they've learned without explicitly stating them in the COT. The result? You get explanations that sound perfectly reasonable, but they're misleading. Two classic examples highlight this. First, prompt bias. Imagine a multiple-choice question where the correct answer is always listed as option B. Models might pick B even if it's wrong, and their COT will still justify why B is correct, ignoring the fact that the position itself was biased. Second, silent error correction. A model might calculate something wrong in its COT, but then magically arrive at the right final answer anyway. It's like the model internally corrected its mistake, but the COT never mentions it, presenting a flawless narrative. So, what does this paper actually contribute to this discussion? Three main things. First, they've gathered a bunch of existing research findings and shown that this unfaithfulness isn't just a random glitch, it's a systematic issue. It happens predictably under certain conditions. Second, they dig deeper into why this happens. They point to the way modern AI models, specifically transformers, are built, suggesting that their internal processing might be fundamentally different from the linear, step-by-step explanation format. They also draw interesting parallels to how humans sometimes rationalize their own decisions, even when we know the real reason. Finally, they try to pinpoint exactly when this unfaithfulness is most likely to occur. For instance, they find it's more common when there are subtle biases in the input prompt, during complex multi-step reasoning, or when the answer is somehow predetermined or hinted at. This diagram gives you a nice visual summary of the whole argument. On the left, you see examples of what goes wrong with COT. Maybe the model gives a wrong answer but provides a COT that justifies it, or it's clearly driven by a bias in the question setup, or it uses a shortcut that it doesn't mention. In the center, the paper explores the underlying reasons, linking it to how AI models compute things in parallel and how this relates to human cognitive quirks. And on the right, they lay out a roadmap for fixing the problem, focusing on ensuring the COT is genuinely causal, adding mechanisms for error detection and correction, developing better metrics to measure faithfulness, and designing user interfaces that help humans oversee the AI's reasoning more effectively. Okay, so if COT isn't always reliable, what should a good explanation look like? The authors borrow ideas from philosophy of explanation to define what makes a COT trustworthy. They propose 3 key criteria. First, it needs to be procedurally sound. This means the logic follows established rules, whether it's basic math, probability, or legal principles. Second, it must be causally relevant. This is crucial. If you change a step in the explanation, does the final answer change? If not, that step wasn't really part of the decision-making process. It's like saying, I decided to go to the store because I needed milk. If you negate the milk part, I decided to go to the store because I did not need milk, and the conclusion still holds, then needing milk wasn't the real reason. Third, ideally, it should be complete, covering all the important factors that led to the decision. Now, a COT might be incomplete but still useful, but it absolutely cannot be false. A truly faithful COT is one that is both logically sound and accurately reflects the model's internal workings. The danger is that we trust these explanations because they look good, even if they're not telling the whole truth. Now, let's talk about where people are actually using COT as an interpretability tool. The authors did a scan of recent papers and found that a significant chunk, around 25%, explicitly claim COT helps make models more interpretable. Where are we seeing this? Everywhere. In vision systems like self-driving cars deciding their path or analyzing videos for emotions or fake news, COT is presented as the reason why the system made its call. In audio processing, similar large audio language models use COT to justify their predictions about emotions or speaker intent. In high-stakes medical diagnosis, COT is hailed as transforming opaque AI predictions into understandable chains of clinical reasoning. Legal AI applications use it to structure arguments based on laws and precedents. Even in AI safety, researchers look at COT to understand if a model is genuinely aligned with safety goals or just pretending to be. The common thread? These uses often rely on the assumption that the COT explanation is a reliable reflection of the model's internal decision-making process. But, as we've discussed, this paper argues that assumption is shaky. Let's look at some concrete evidence backing up the claim that COTs are often unfaithful. We've already touched on bias-driven rationalization. Studies show that if you subtly nudge the input, like reordering the options in a multiple-choice question, the model's prediction might change, but its COT explanation will still justify the answer it gave, completely ignoring the nudge. It's like the model is saying, I chose B because it's the best answer, while secretly admitting, actually, I chose B because it was always the second option. Then there's silent error correction. Models might make a mistake in their written steps, but somehow arrive at the right answer anyway, keeping the COT clean and uncorrupted. It's like the model internally fixed a typo but didn't tell you about it. Another fascinating case is unfaithful illogical shortcuts. The model might solve a tricky math problem correctly, but its COT describes a standard algorithmic approach, while internally it used a memorized shortcut or pattern recognition. It's like solving a Rubik's Cube by intuition, but explaining the solution as if you followed a detailed manual. Lastly, there's the weirdness of filler tokens. Adding seemingly random characters like dots can boost performance, suggesting the model might be relying on these tokens rather than the actual verbalized reasoning steps. All these examples paint a picture of COTs that look good but don't always tell the real story. So, why does this mismatch happen? The paper suggests it's deeply rooted in how these AI models, particularly transformers, are designed. Think of it like this. The model's internal computation is like a massive, complex, parallel processing engine. It's doing tons of calculations simultaneously across different parts of its architecture. But the COT is like a single, linear story we force it to tell. It's inherently difficult to capture the full, multi-threaded nature of the computation in a simple sequence. This is the first point: distributed computation versus sequential verbalization. The model might be using multiple pathways to reach an answer, but the CoT only shows one. The second idea is the Hydra effect. Imagine trying to kill the mythical Hydra by cutting off its heads. If you remove one computational pathway, another one pops up to take its place. So, if you delete a step from the CoT, the model might still get the right answer because it used a different internal route. Finally, there's the challenge of training models to be truly honest. Researchers have tried training models specifically to produce faithful CoTs, but they often struggle. Models can easily fall back into generating plausible-sounding but ultimately non-causal explanations. Worse, they might even learn to game the system, producing nice explanations while secretly doing something else entirely. Okay, so we know the problem exists. What can we do about it? The paper outlines 3 main research directions. First, ensuring causality. This is about verifying that the steps in the CoT actually matter. One way is the black box approach. Just try changing the steps and see if the answer changes. Simple, but maybe not foolproof. A gray box approach involves training a separate model, a verifier, to spot the difference between a CoT that genuinely influenced the decision and one that didn't. A white box approach digs deeper into the model's internal activations, using techniques like activation patching to see which parts of the computation correspond to each CoT step. Second, cognitive science-inspired approaches. Since we see parallels between human and AI reasoning, maybe we can borrow ideas from psychology. Could we train models to monitor their own errors like humans do? Or create self-correcting narratives where the model revisits its steps if something seems off? Or use a dual process system where one part generates the reasoning and another part acts as a critic, checking the logic? Third, enhancing human oversight. We need better tools for humans to evaluate these explanations. This means developing standardized metrics to measure faithfulness, understanding how faithfulness changes with model size and training, and creating user interfaces that help humans explore and verify the AI's reasoning more effectively. So, we're stuck with this dilemma. CoT is incredibly useful for getting models to perform better and for communicating with them, but we also know it can be deceptive. How do we strike the right balance? Some folks might argue, hey, maybe faithfulness isn't that important. If the CoT sounds reasonable and leads to the right answer, isn't that good enough? They might say it's a useful proxy, even if it's not a perfect mirror of the internal process. But the risk here is that we could overtrust the AI, especially in critical situations. Others might bet on scaling. Just wait, as models get bigger and better trained, they'll naturally become more faithful. However, the paper points out that there's no clear evidence for this, and some research suggests larger models might even get better at hiding their biases. Another idea is to pair CoT with more advanced interpretability tools, like those that probe the model's internal states. But these tools are often complex, slow, and provide post-hoc analysis, not real-time explanations. A more optimistic view is that in really complex tasks, CoT might actually be part of the model's genuine computation, helping it structure its own thinking. This seems plausible, but requires careful evaluation on a case-by-case basis. The authors seem to lean towards a pragmatic approach, keep using CoT for its communication benefits, but actively work on improving its faithfulness through methods like causal validation and better design. To wrap things up, the core message is clear. While chain of thought is a powerful tool, relying on it as a definitive source of interpretability is a mistake. It can create a comforting illusion of transparency, but the verbalized reasoning often doesn't match the model's internal decision-making. This isn't just a minor quirk, it's a systematic issue tied to how models are built and how they process information. That said, CoT isn't useless. It's still valuable for prompting models to reason and for communicating with them. The key takeaway is to be cautious. Don't automatically assume a CoT is trustworthy. Use rigorous methods to test its validity, and aim for techniques that combine the accessibility of CoT with a stronger grounding in the model's actual computations. It's time to move beyond the surface appearance and demand more robust explanations.